Today we're going to look at the parent function, the square root function. So to talk about this function, we're going to look at a handout I have where we're going to look at this function by investigating its tables, looking at the graph, and checking out its transformations. So this handout begins by having us look at the parent function, which we call p of x equals the square root of x. So if you actually try to evaluate this function at different values, there's actually an issue with the square root function. The square root function is undefined at certain values. You would find out that when you take the square root of -2, you get an expression which is known as undefined. So this expression here in the table, we would just say it's undefined. And the same thing happens with -1. The square root of -1 is also an undefined expression, so this would also be undefined. So what that means is the function does not exist at these values of x. But as soon as we get to 0, you can take the square root of 0, and the square root of 0 is 0. Right, because 0 times 0 is 0. And we continue, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, and right, we have our squares that I gave us in the x values here, so this would be 4, 5, and 6. So let's go ahead and graph these points. The undefined values are not points on our graph, so I'm not going to graph any x values below 0. So we're actually just going to start at 0. So 0, 0, 1, 1, 4, 2, 9, 3. And I can't fit any of the other points on my graph, so we'll just stop there. And if you graph this with a nice smooth curve, it actually looks a lot like the quadratic pattern, but it's sideways, right? It moves horizontally instead of vertically. And it asks here, what happens with the negative x values of this function? Why did we skip certain positive x values? So the main takeaway is, if you look at my table I gave us, when x is negative, square root of x is undefined. And to address the second question, why did we skip certain positive x values? Well, if you can see here in my table, right, like in between here and here, I jumped from 1 to 4. And the reason why I jumped from 1 to 4 is because the square root of 2 is an irrational number, so it's a decimal, like 1.4 something. So I only wanted to address the values that we could graph that are nice. But the main idea is we skipped certain positive x values just because we want integer function values. So not all values of square root of x are integer values. This table has us look at transformations of the function. And to do these transformations on the table, what you'll notice is all of these have the square root of x function, which we have on the table above, on the handout that we just started looking at. And all we're going to do is just add a certain value to it. So actually, let me zoom back out here. So what you'll notice is, in my original table for square root of x, for -2 and -1, the function's undefined. So for all of these functions, f of x, g of x, and h of x, all of the first two values are going to be undefined. So undefined, undefined. And that's because if the square root of x is undefined, it doesn't matter if we're adding or subtracting from that value. All right, but then we get to 0. So let's talk about f of x. Square root of 0 is 0, but then when you add 4, this would be 4. So literally, this is from this value here, and when you send it over here, you're just adding 4. Similarly, for g of x, square root of x minus 6, this would be 0 minus 6, so this would be -6. And again, that's from this value here, right? 0 is the function value, but when you subtract 6, 0 minus 6. And lastly, square root of x minus 3, so 0 minus 3 is -3. Now, as you continue on in the table, you're just taking the function values that we have from before, but you're just adding 4. So if I were to look at all these values, 1, 4, 9, 16, 25, 36, we have all the values up here, right? So we want them to be for this function, but we're just going to add 4 every time. So before we even look at the next functions, just to have an idea of why we're looking at these different functions that are based on the original parent function is graphically you can see that there's a transformation happening. So let me plot these points on this graph I have here. All right, so we're undefined at -2 and -1, just like the previous function, the parent function. But this function starts at 0, 4. So 0, 1, 2, 3, 4. And then it goes 1, 5, 4, 6, and 9, 7. And that's the last one I can fit on my graph here. And what you'll see is we have the same graph as the original parent graph. But instead of starting at 0, 0 as that initial point where we started the function graph, it just happens to be shifted upwards. This is called a vertical transformation, a vertical shift. And it actually just moves up 4. And that's what this table is trying to illustrate. When you add 4 to the function values, what's happening graphically is that's actually moving the function vertically up. Let's take note of what's happening with this function g of x, where it's the square root of x minus 6. So it's the same function values as before, but we're subtracting 6. So this would be -5. And I'll let you refer to the original table to see where I got those values. But okay, this starts at 0, -6. 1, 2, 3, 4, 5, 6. And it goes up by 1. The next point, and then it goes up by 1 over 3. So it has the same shape, but this one got shifted downwards. So as you can see, because it was the parent function -6, this moves down 6. So I'll leave it for you to go ahead and look at and finish the table for h of x and graph it. So what transformations do you see in these functions? All the functions now we have 2 more tables. They're a little smaller this time, but it's only just to exemplify what's known as a horizontal transformation. So I have these tables pre-made for us where we're going to look at a of x and b of x. And let's go ahead and look at this expression here. Square root of x plus 8. So for the square root of x plus 8, if you plug in -9, this would be the square root of -1. Well, previously we saw that the square root of a negative value is undefined. So this table begins with an undefined value. But in the next x value, we have -8. So -8 plus 8 is 0. So we have a square root of 0. Well, this is where it starts at 0. And the next value is -7 plus 8 is square root of 1. And we would have the same shape of the parent function, but now because my x values are changing, this is going to be an x-axis shift, right? A horizontal shift versus a vertical shift. So actually, let me just go ahead and graph a of x first. So the undefined value is at -9, but at -8, we have the beginning value of our function. So -1, 2, 3, 4, 5, 6, 7, 8. And then at -7, it goes up 1. And I know my table doesn't continue, but if I kind of copy the same shape as the previous functions we've looked at, the next point will go up 1 over 3. And the next point will go up 1 over 5. And that's our function a of x. And what you're hopefully noticing is instead of being an up and down shift, this is actually a function that shifts the parent graph left. Okay, let's look at b of x. So b of x, we kind of have the same thing going on. If you take 4 minus 5 inside that square root, you get -1. So the square root of -1 is undefined. The square root of 5 minus 5 is square root of 0, which is 0. And the square root of 6 minus 5 is 1. So square root of 1 is 1. So this is showing a shift of the parent function in a different direction. This is actually going to start at 5, 0. And then the same pattern, up 1 over 1 and up 1 over 3. And there's no room to fit the rest of the function, and that's okay. It would look something like this. And that's b of x. And that obviously moves 5. So right, 5. So why do we have to use new x values? How should we choose them? So we have to use new x values because if we use the standard x values from before, some of them will be undefined and we don't have perfect squares. So what we had to do is shift our x values so that we find where the defined values are, and then we want to find the next perfect squares based on that. So what transformations do you see in these functions? These are what we would call horizontal shifts. Okay, we have another table where we're going to look at what happens when you multiply a factor by your parent function. So all of these square roots begin with an x value of -1, and this is just to reiterate the point that the square root of a negative value is undefined, so all of these will be undefined, because you cannot take the square root of a negative when you're looking at a real function. Okay, so the square root of 0 is always 0. So all of these will also be 0. So 0 times 2 is 0. 0 times 3 is 0. And 0 times -4 is still 0. Now, if you go back to the previous tables, I handpicked these x values so that we're getting the perfect squares, right? The perfect square that makes 1 is 1 squared. The perfect square that makes 4 is 2, right? 2 squared. These would all be the same values, right? 1, 2, 3, 4, 5, 6. But they're being multiplied by a factor of 2. So this is just all of those square roots times 2. So this would be 1 times 2, 2. 2 times 2, 4. 3 times 2, 6. So this is the same pattern, but times 2. Right? The next function multiplies these by 3. So in the way I've made this table, it's just counting by ones, but then when you multiply by 3, it's multiples of 3. So 3, 6, 9, 12, 15, 18. And lastly, the last one has us multiply by a factor of -4. So we multiply those same numbers by -4. So we're just going to look at multiples of 4 going negative. And I would leave it for you to use a graphing utility or go ahead and sketch these graphs. What you notice is it's not doing the same thing we saw before where we're actually like moving the function up or down or left or right. This is doing what's called a vertical stretch. So it says, how would the graph of these functions compare to the graph of the original parent function? These would be vertical stretch transformations. So vertical stretches of square root of x. But something to add is because h of x has a negative factor that we're multiplying by, this would also apply an x-axis reflection before we start stretching the function. So I would also add h of x also applies an x-axis reflection and stretch. And again, I would leave it for you to graph it or to look at a graphing utility to kind of illustrate what this table is trying to show you. Now from here, I just made a little kind of like review of the function values that we've been playing with. So this a value is what we just did, like the vertical stretch value. The h value inside the square root is what we did when we saw the horizontal shifting, and the k value is what we saw when what we messed with when we wanted to do vertical shifts. So how does the value of a affect the square root function? This affects it by applying what's called a vertical stretch. And as we saw with h of x, it can also cause an x-axis reflection. The next one says, how does the value of h? Well, this affects the function by a horizontal shift. And lastly, how does k affect the function? This is known as our vertical shift. So based on the square root function, if you put values a, h, and k into the function, you get these 3 different effects. Using descriptions of transformations to write functions. Use the description of transformation to write an equation from the parent function. So it says shift the square root function down 2 and left 4. So this is based on this function right here. So since we're only going to shift it down and left, we don't worry about a, we're just going to play with our h and k. So I'm just going to go ahead and write the square root of x and then plus, and we just have to figure out what's going to happen here. So to move it down, that means we have to subtract a k value. So this would be -2, right? Down 2 would be adding a negative value. And to move it left 4, if you notice in the transformation function up here with the a square root of x minus h plus k, the h value is being subtracted because the horizontal shift is a negative of the actual coordinate where the function begins. So since it's left 4, which on the x-axis is -4, this would actually be +4. right? Because if you actually plugged in, I'll actually just show it. If I were to write the original function, if I were to write the x minus h, right, x minus h, and I replace h with -4, hopefully we know our rules of subtraction. When you subtract a negative, this would actually become +4. So this function would be the transformation that I'm asking for. Okay, the next one says to shift the square root function up 9 and right 1. Okay, to make it move up 9, we're going to add 9. And to make it move right 1, it would be x, and it would be -1. And I would leave it for you to look at a graphing utility if you wanted to confirm that these functions are actually the transformations that we're looking for. Okay, so in all of these, they're based on the parent graph. So let's look at M. All right, so in this function here, we have this point here where the function begins. This is 3, 4. So since it's moving right and up 4, I know my k value is 4. And so it's moving right, this would just be 3, right? Because it's -3 from the x coordinate of this point, 3. In the next function, this point here that it begins at is -2, -1, 2, 3, 4, 5, 6. So if I were to try to develop my square root function, well, it is moving down, so I know my k value is a negative, so I'm going to write -6. I know that the function has to move left 2, so if I were to call this x minus a -2 as my h value, this would be +2. And lastly, what you'll notice is this function doesn't have the same pattern as the previous one. This one's actually has an x-axis reflection, right, before it got shifted. So this would actually have a -1 factor in front because it's not stretching it, but it did do an x-axis reflection before the 2 shifts were applied. And lastly, r of x over here, you'll notice it only has a horizontal shift. So this would just be x, and since it's moving right, it's minus, and it moved right 1, 2, 3, 4, 5. So this is 5, 0. So x minus 5 would be the expression inside the square root, and that would be that function. Okay, lastly, we're just going to graph a few sketches. And again, you can use a graphing utility to confirm these sketches. All right, so the first one, we're going to graph f of x equals 2 times the square root of x plus 4. So the main idea is the only shifting that's happening is this +4. So I know that at +4, this will be where my square root begins. Now, if I were to just graph the square root of x that moved up 4, it would have the next points that look like this. Here, here, and 1, 2, 3, 4, 5. So that's the standard pattern of square root of x. So just as a quick note, these points would represent the square root of x plus 4. But my function is 2 times the square root of x plus 4. So yes, it's getting shifted up 4. It has the same beginning point as this point here. But because the function is getting multiplied by 2, what happens is all of these points double their distance from the x-axis before you shift it. So this point here is a value of 1, but 1 times 2 is 2. This point here has a vertical distance of 2 from the x-axis before the shift, so this would now be at 4. And this one has a distance of 3 from the x-axis before shifted, so now it would be up here, let's say at 6. So that's what it looks like when you vertically stretch the points of a function. They get multiplied by their original distance from the x-axis. So my function would look something like this. So that would be f of x. So again, I only use the square root of x function to just illustrate what it would look like if you didn't stretch it and then we stretch it by a factor of 2. Okay, g of x says we have a square root function that's going to shift right 1, right? This would shift it right 1 from the origin, and this would move it down 2 from the origin. So my beginning value for this function would be right 1, down 2. Now, remember, if this was just square root, the next points would be here, here, and here. But since it has a negative value in front, right, a negative, it's just going to do an x-axis reflection. Again, before the shifts, so think of it, if this was the x-axis before the shifting, all the points would reflect upside down along that axis there. So these would be across the axis the same distance. So that would be the function we're looking for. That would be our friend g of x. But again, this function up here, that would be square root of x minus 1 minus 2. Right? Because that one did not get the x-axis reflection, but g of x did. I'll get rid of all my extra functions here. And lastly, we're going to graph h of x, which just has a shift of right 7. And there's no other function transformation. So 1, 2, 3, 4, 5, 6, 7. And then the standard pattern after that is up 1 over 1, up 1 over 3. Can't fit any more points. And there it is. That would be h of x. All right, so I hope that helps you understand the parent function, the square root of x, along with some of these transformations.